All right, I think we're going to get started. I want to thank our panelists. My name is Rich Brueckner from insideHPC. Can you hear me? Does it sound okay? Okay. Virtualization in HPC is a very interesting topic. And I did a presentation once in Taiwan, and I was told that the proper way to introduce yourself is to first say that you're not worthy of the audience. And then you make a joke. And then you've started out things right according to the culture. So I am not worthy. This lineup of panelists, I write about HPC and virtualization and big data every day, but these are the guys doing some very groundbreaking stuff. So just wanted to bring that out. What we're going to talk about today with this topic, was virtualization ever going to happen? And a lot of people, from my experience, are saying it slows things down. It slows things down. We can't have that in HPC. That's the whole point. Well, there are examples today where things actually run faster in virtualization than on bare metal. And I don't know if any of our panelists are going to attest to that, but I've heard the use cases. And, okay, well, we won't have a debate here anyway. So maybe that was my joke that I was supposed to tell. Yeah, okay. Yeah. So let's get started. What I'm going to do is, we have an interesting use of duct tape here, but two microphones to make sure that the camera hears everything. If I could just have the panelists introduce themselves, where they work, and then hand it down. So start with you, James. You need to hold it very close to your
Very
mouth.
close. Okay, can you hear me all right?
Yeah.
Excellent. So my name is Jim Wilgenbush. I'm the director of the Research Computing Center at Florida State University.
Hi, my name is Paul Calleja. I'm director of high performance computing at Cambridge University.
Hi, I'm Joseph Antony. I run the cloud and online data services at the NCI, which is the HPC center located at the Australian National University.
Hi, my name is Brad Dispensa. I'm the director for the Institute for Human Genetics at UCSF.
My name is Brett Zimmerman. I run the cluster machine for the University of Oklahoma Supercomputing Center.
So I don't have slides either.
Great.
So I'll just kind of tell our story for how we started doing this and where we are and what we're trying to do.
Yeah.
So essentially, the reason that we started looking at virtualization was because in genetics and a lot of life sciences research, a lot of the technology is moving very quickly. And a lot of the software that's being developed for the computational clusters is written by graduate students or written by folks that are working on their thesis or postdoc. So it's not always the most stable code. So we had an increasing number of users that wanted to start running what we thought was highly volatile code on a system that had been stable for years and years and years, and we really just didn't want to have people running janky code. So the first thought was, well, we could carve off a segment of the cluster and allow them just to use dedicated machines, but then we're losing total cores for other projects. So we started partnering with VMware to start coming up with a model that would allow our researchers to have sort of a sandbox type environment where they could stand up clusters that would be imaged in a way that we could control, but that would allow them to run code that maybe we wouldn't let them run normally. And it started getting a lot of interest in some of the academics in our institution. And the majority of the reason is because folks want to do stuff in cluster environments like that you would never let them do. Like, I want to be root. Like, no, I'm really sorry, but we're not going to let you do that. I want to run Ubuntu. Super. We're a RHEL shop, so that's not going to happen. Or they want to run something else that just it's either a bleeding edge version of a particular package, and they don't want to have to self-compile in their own directory, or there's some other extenuating circumstance. So that's kind of how we first got it started. What we ended up doing was that basically we have a Dell blade chassis that we have populated with some blades, and we have an Ecologic environment that we use to store some of the VMDKs. And what we wanted to do basically was allow our research staff to provision templates that we control that conform to the university's image, but still let them function. And the big takeaway there is, okay, well, great, why didn't you just use Amazon then? Or why didn't you use some other cloud provider? And the reason is that in genetic data sets, the data sets are very large, so it's multiple terabytes. And for some of the studies, it's thousands of patients, so it's hundreds to petabytes worth of data. So moving that up into the cloud is not really cost effective. The meter starts running when you run it in, the meter is running while you're doing the analysis, and the meter is running while you take the data out. So we didn't think that was a great thing. The other thing is that the university doesn't treat all genetic data yet as truly HIPAA yet, but IHG is unique in that we've always treated our patient's genetic sample as if it was identifiable data, so we treat it like HIPAA data, and we didn't want the possibility of a breach to basically allow someone to get this data that maybe not today, but maybe tomorrow could be used to identify someone, and because of the volume of data, again, hundreds of thousands of people, we didn't think it was a good risk. So we opted to run it locally. And what we're trying to do now is basically find where the applications are that work the best and where the applications that don't work well. So obviously anything that relies on direct control of the InfiniBand controller, that doesn't work so well at the moment. You can do direct pass-through for one host to the individual device, but that's it. So you can't have parallel sharing for like 6 hosts on one blade. There's some efforts, I know, for the KVM side of the house and OpenStack, and I know VMware is working on something as well, but it's not out yet. And I think it's something that they're trying to do, but that's, I think, the biggest Achilles heel so far is that there's no true InfiniBand support. But in most of the life sciences stuff, you really don't need it that much. Most of the research clusters can get by on a 10 gig network. It's not really so latency specific. So we're finding that where the trade-off is you maybe lose a little bit of speed on the storage side, you more than make up for it in the fact that you can completely customize your environment, save it, and then only pay for what you're using. So you're only going to use it for 3 weeks. Don't spend that huge amount of CapEx on buying infrastructure in your grant. Just say, I need like $3,000 to run for 3 weeks. And then can you guys make me a snapshot when I'm done so that if we get called out on a paper or something like that, we can recreate the environment and bring it back exactly. And that's sort of been the other big popular thing is that in a lot of clusters, you have to sort of overwrite your software after whatever your refresh cycle is. So that version of Python that we used to write that paper maybe isn't installed on the cluster anymore. But in this environment, I can bring it back to exactly the same place that it was when they wrote their paper, and they're more likely to be able to exactly reproduce the data that they had at that time. So that's kind of where we are.
All right. Well, Brett, do you want to go? Are you ready?
Yeah. Okay, apologize for that. There was a conversion problem with my slides, and I'm working off my notes here, which I had to get up because I have a really, really bad memory. So I'm not sure what all I add to this discussion. We're doing this in a very rudimentary kind of way at OU. Our first run at virtualization was actually way back when we, like any institution, have a large number of computer labs scattered throughout the campus, and in order to harvest compute cycles from those, we were running Condor in a virtualized Linux environment for throughput computing. From that, we went to bringing support virtualization into the cluster network environment. We are getting into running a dedicated OpenStack cluster, which we are using to provide democratization of image. The drivers that we're getting from our researchers are the things you touched on. Being able to pin a compute environment at a specific point in a way that we can't on the general cluster. Being able to archive virtual machine images that are used to run a job for as part of a research group's data management plan. being able to exchange virtual machine images with peers at other institutions and having a unified virtual machine image that they can run at different centers. We are, in order to get the resources out there to drive adaptation or adoption with our research community, we are running OpenStack, Nova Compute side by side with our batch scheduling system, and allowing OpenStack to have sort of the run of the house, and using load index monitoring to pull back the batch scheduling from nodes that are engaged with the OpenStack computing process. So that's kind of where we're at.
So just a little bit of background to give you some context into why we're interested in virtualization. So within the university, there's three main functions that keep me busy. We run a traditional university computer service where we provide resources to the academic staff. We also undertake our own research on HPC systems. We run a Dell Center of Excellence where we develop systems and promote those systems to the community. And we also run a commercial HPC service, kind of HPC as a service to industry. And that's specifically funded by the government to try to promote HPC to the industrial sector. Okay, so there's the three areas of work. I'll skip over these ones. This slide is really to show that the HPC services I provide are for the university, but also for the tech bubble around the university. So there's around 1,500 tech companies in a 15-mile radius of the university. We have a mandate to promote high-performance computing to that tech bubble and to the university. One of the main drivers that forces me to look at virtualization is our business model. So we do not run as a subsidized HPC center. We run as a cost center where we have to charge our users for services. So we get zero subsidy from the university. Okay, so we gain no central funding, and we have to pay all our explicit costs. The only subsidy we enjoy is we don't pay for the capital cost of our machine room. Yeah, so the machine room infrastructure in that building I did not pay for, but everything else we pay for, and we get no money from the university. So we unitize our resources and we sell them to academics under contract, and we also sell them externally. Yeah, so this is an odd business model. I don't know many centers that operate like that. So we started this 7 years ago, and we were given £2 million for capital, and then we had to work that capital ever since and make the books add up. And we've been running for 7 years under that model, and we've increased our capital turnover by a factor 2 in those 7 years, and our operational turnover has gone up factor 4. So there's been a reasonable growth in revenue over those 7 years. So obviously we provide traditional shared resources. So we have a large central computer system that we make available. We also provide consultancy services for the academics to go and build their own solutions, and we provide hosting services. Traditionally, we come from the large kind of scale-out compute pedigree, and we're moving more into data analytics. Most of our growth is now in data-centric analysis away from simulations. So all our new growth is coming from data sciences more than simulation sciences. And it's these customers that are driving us towards virtualization. I'll skip this one. This is just, we've got lots of Dell servers, basically. So I guess this is what you're really interested in. And because of our business model, we need to increase accessibility to HPC. So we need to make HPC more accessible to a wider audience. If we don't make HPC more accessible, I don't get enough customers and I can't pay my mortgage. And so we need to make HPC, we need to move HPC away from that very small number of large power users. Yeah. Because most HPC directors won't tell you that 95% of their resource is used by 5% of their users. And so we all put slides like that up saying, I've got 700 users, which I have, but 650 of them aren't doing anything. Right? And this is a general unspoken secret in HPC centers. And we have to change that, otherwise I'm out of a job. And so we have to make HPC more accessible. Okay. Also, we need to increase our customers' productivity, because if they can't get much out of it, again, they're not going to pay me for it. And so we need to make it more accessible, and we need to make it more productive. And increasingly, we need to think about security of a multi-tenant solution. Yeah, so when I have multiple tenants on my infrastructure, they are becoming increasingly nervous about what other tenants are doing on that infrastructure, in terms of their data, especially when we start moving into life sciences, and I have medical records, and I have genomics records, and I could end up on the national news if these things leaked out. And customers are bothered about that, especially our industrial customers. We work with Jaguar Land Rover, with Rolls-Royce. These guys don't want their car designs ending up in the wrong place. So these are the kind of the feature sets that I'm looking for, and virtualization potentially helps to deliver these feature sets. So virtualization holds the promise of flexible access to the users. It allows people customized environments. That's exactly what you were saying before. I can sandbox that user, so I can protect my customers from other people, and I can protect other people from my customers. And so this is interesting. So we've been running what I call an HPC club for many years, where if I trust you and you're in my club, I let you on. If you're inside my organization, of course, you should do as you're told. But if you're an external company, and I let you on my system, I should be careful. And we have industrial users, and those industrial users currently are just people in my club. But if I want to open a shop, then that's a different problem. And sandboxing gives you a way of protecting yourself from malicious customers. Also, of course, it gives your customers more choice. It democratizes their HPC consumption. If they can run on my cloud, they can run on Amazon's cloud, and then they can go to a service that gives them best value. And again, your users feel less trapped by you. They can take advantage of Amazon's spot price on that day if it's cheaper than me. That's important. People feel they want that. Okay. It also gives me the priority to the option of having a more dynamic workload. I can checkpoint out jobs if that person's not paying me much, and I have a more high-value customer coming in. I can checkpoint out the guy that's not paying me much, and put someone in front of him in the queue. So it enables me to have quality of services which are quite severe for people that don't give me enough money, which is good. And also importantly, it enables us possibly to move away from HPC niche software, where I've only got one guy in the whole of the UK that can run that stack, which is a problem when he goes and works for a bank. I hope this gives the promise of HPC software stacks becoming more mainstream, which is necessary. So what are we doing in this area? There's 3 use cases that I'm interested in. The first one that we have quite a lot of experience of is using virtualized platforms for remote visualization and using virtualized platforms for virtual workstations. So now with new developments from companies like VMware and Citrix, the VM can get access to the 3D accelerator through the NVIDIA card. This is kind of cool. So you can use this for traditional remote visualization, where you have all your data's in the data center, and your user is somewhere in the physics department on the other side of town, and he wants to do that remote viz. So these platforms can do that. And of course, these platforms also offer your users secure ways to look at their data. So all that medical imaging data, I don't want that guy logging on and downloading that data. But if I let him just use that from a virtual session just over a pixel stream, he can't do anything to the data. So it enables security and flexibility for accessing the HPC systems. So we've been running these systems for some time, and we have some white papers coming out through Dell that describe that. Of course, the second use case is more traditional, where we virtualize the HPC platform. We're investigating several stacks on that now. We do not have that in operation, but we have something in dev. So that's traditional HPC for throughput computing. Obviously, the large parallel workload, there are still inefficiencies through the Mellanox stack, which are work in progress. So we flip the things into Ethernet mode and do it that way. But I think that will develop, and Mellanox are putting a lot of effort into that. And the third area, which I think is more interesting, is for data analytics platforms, where you have a large data set. Okay, you can't take the data to the people. It's not possible. So you want to bring the people to the data. Okay, and if the cluster that's attached to that data is virtualized, it enables your customers to bring their tool chains and their canned VMs to the data. So for your customer, when he's running, it's like his own virtual private cluster. He can have root access, which they always seem to think they want, and they can have their own environment. And for them, it's like having the data in their lab. And they tear their system up, they interrogate it, and they tear it down. And it's also sandboxed for them. And that's actually much more, I think, useful than the traditional HPC platform as a virtual service. It's data analytics as a service, I think, is more important.
All right. So you're going to hear some of the same use cases, some of the same architectures and so forth, but so that, move it a little higher up? Okay, that's probably better. I think what I can bring is just another view of sort of context. So why are we deploying this in our particular environment? So to start with, for context, what is our environment? So I'm at Florida State University. We're a fairly typical U.S. state university, fairly large. We're located in Tallahassee, Florida, which is in the panhandle of Florida. We have 15 colleges that we support, 39 centers, institutes, a medical program. We have 7,000 faculty at Florida State, about 40,000 students. That includes graduate students. So it's a fairly typical U.S. public institution. In addition, like some very much research-focused institutions or universities, we also support a national lab. This is the National High Magnetic Field Laboratory. The environment that I manage is interesting, but it's actually fairly common also at universities that have decided, made institutional decisions to support research computing. It's a fairly diverse ecosystem of resources that we can sort of capture in a very high-level schematic. We work on the notion that essentially one size doesn't fit all. As Paul said, our little secret, though, is that most of our actual resources are right here. That's what we spend our money on in terms of cooling and electricity. But the fact is, actually, we invest a lot of time and effort on these other resources because I found that it's impossible to do multidisciplinary research if you take a one-size-fits-all approach and you say, look, we've got this beautiful HPC platform and it does LinPack benchmark at this fantastic rate, eat it. And that's not the approach that we've taken. So we spend a lot of time developing these other pieces, including high throughput computing. We use the Condor platform to actually service a number of our users. For remote visualization and interactive computing in a non-scheduled environment, we actually still use bare metal, but we use an interface called NX No Machine, similar to other centers also. And then more recently, we've actually brought up a platform that I'm sort of boxing here as our DB and our web platform. That's our virtual platform, and I'll describe the architecture of that system in a moment. Our resources actually map back perfectly to that schematic if you go to our website, so you can dive deeper into actually what those resources represent and how much they cost. That information is publicly available, so our resources can easily see what rate, if they need dedicated access to those resources, they'll have to pay. All of these resources except our virtual machines are available also on a first-come, first-served basis, which is important for new faculty in particular. They can come on board without any investment in funds or graduate student cycles. They can get up and running fairly quickly, get a feel for how the system works for them, and then if need be, they can dedicate some of their startup funds, or if they begin to actually bring in external funding toward dedicated requirements. So all of these services are available for free except the virtual machines. This is what our actual virtual stack looks like. So we're actually investing a lot of time and effort in the OpenStack framework, LiveVirt, and KVM as our virtual system. So again, the sort of drivers behind this are very similar to what we've heard already, so I'll just sort of spell this out in bullet points. One of our primary drivers is very often we have researchers who just need root access for a variety of reasons, and we've heard some of those already. Some of those include evaluating new software that we're not going to support on our HPC platform because it's going to bring down the system, and that doesn't make our other users happy. There are other operating systems also that we're not going to support. We heard Paul allude to that, and that's Windows is a case for that. Very often, actually, we need to bring up web portals for them to interface with actual other components of that ecosystem that you saw. So we have many users actually who've brought up very simple sort of PHP interfaces so that external users can use their algorithm and actually tap into their own queue in HPC. Right, so that's sort of our driving use case. What we are not is we are not sort of a general place for hosting someone's brochure website. A lot of people come to us with that interest, and we move them to our central IT organization. That's not really what we're about. The way that we essentially control that access is we ask what other resources within HPC are they using, and that's usually a fairly low benchmark for them to pass. For example, data storage is often sort of a driver for a lot of our resources. We don't claim at this point, for all the reasons that you've already heard, that this is a robust substitute to our high-performance computing platform. There are issues associated with that, and again, that's been described already. It is available to all faculty members, but for right now, it's only available on a buy-in basis. So we'll bring up some virtual machines for initial testing, but the expectation is that you do actually provide funding for that. The way we do this is probably, again, sort of similar to what other users are doing, and this is very attractive to many of our customers of this particular service, is they're able to sort of mash up resources according to how they need them. So they can buy a chunk of our Sky resource, and they can virtualize it under a very large system or break it up into various small pieces. Particular use cases, this really speaks to broadening representation in research computing. If you see what I've done actually is sort of try to define the function and then the business unit actually associated with this. So we have College of Business, College of Social Work, College of Communication and Information, our College of Medicine, the Antarctic Research Facility. By the way, in Tallahassee, Florida, if that seems odd, we can talk about that later, but it's really there, and it really is frozen core samples. It's pretty cool. Department of Biology, and then actually these last ones are my projects that are NSF funded, where I needed to actually show some immediate results for some of the work that I'm doing and make actually some of the algorithms that I'm working on available immediately to external users. So these are the sort of driving cases, and I think represent pretty clearly that it broadens the set of users that are typically using research computing facility. Contact information, you can get me here. We're also available via these social media.
So while the slides come up, I thought I'd paint the scene. We have a machine in the top 500. It debuted at number 24. It's right now dropped to 32. But the key problem there was grand challenge problems run on this machine. But there are a lot of people who do very good science. You know, these are the guys who turn out the Nature and the Science papers. And a key driver for us was, how do we support these guys, right? Plus big data. So I'm hoping to give you a flavor as to why we moved into HPC and virtualization. So quick blurb who we are. So our mission is to foster ambitious and aspirational research objectives within the Australian context. So very quickly, we have government funding, we have the National Science Agency, but the real way we engage with research communities is essentially research outcomes and then translating that into something down here, which is storage, HPC, or cloud. So a couple of the things that happened was flexibility of environments. And I stole some slides from one of our chief investigators. For them, they came to us and essentially wanted to set up a climate center of excellence which captured code, data, as well as compute. So the way they looked at it was they needed an integrated, intimately connected system which was robust and accessible. So Rygen is our HPC system, our cloud, and then we work with these teams. So, essentially, we have a unified model which is used for operational weather forecasts. So if you see the weather forecast in Australia, it comes from a model called Access, and this is from the UK Met Office. That same model is also used for research activities, right? So we host the source for that. And importantly, if you were there for the keynote speech today morning, this was talking about the CMIP5 data processing. So we actually are the Australian node for that. So this is a lead-in into why we need this. So in case you're wondering where we are, we're at the capital. It's not Sydney. We're between Sydney and Melbourne. So mind you, this is my take on why we've gone on to HPC virtualization. So this mirrors comments from a lot of my colleagues here. HPC procurements typically involve major capex, and this is big iron for grand challenge problems. And typically what you find is you'll have most centers having a capability machine and something that does work for everybody else. So the capability machine will get them into the top 10, 20, but then there's this workhorse, which is typically lots of x86, some InfiniBand. So I class this as pets and cattle. Why? Because I was at the OpenStack Summit in Hong Kong, and this came up from the guys at CERN. So from a virtualization perspective, there are two modes. One is pets. You love them, you give them names, you lovingly take care of them. When they get ill, you nurse them back to health. Whereas cattle, well, they have a moniker like VM42. If they're ill, you just take them out the back and shoot them, right? So it's this idea that you want to have HPC clusters on demand for the masses. We want to democratize this, right? So that's one side of the puzzle. One side of the motivating factor. The other thing is this looming iceberg, right? I'll try to sketch this out. So there's our center up there, Her Majesty's Australian ship, HMAS HPC, hitting this iceberg. Essentially, it all started with climate data processing. It started off with the need for lots and lots of storage. So these guys, essentially, their requirement was initially 200 terabytes, please. Then it shot up to about 5 or 6, and right now we're at about 20 petabytes. And the real reason for this was because there was all of this stuff happening at the back end that we didn't envisage or foresee a couple of years ago. So this is all around the reuse of data. How do you manage metadata, a priori analytics? I have no idea what's going to happen in a couple of years. Somebody might come up with a new algorithm. They may have their virtual machines in cold storage. You need to bring them out, respin them. There's deep storage. You have multiple communities. So I found a much nicer slide, and it's essentially this, where it's the velocity, variety, and volume. So our center had to rapidly expand file storage, for example. So we're currently at about 20 petabytes of just Lustre. This is Lustre that's going to be across all of our infrastructure, and there's tape at the back end, etc. So I believe HPC centers will be forced to evolve beyond batch-oriented systems. So, and primarily, I believe this is because of big data. Back in 1999, we were forced to handle non-traditional workflows because of complex data lifecycle. So I'll quickly go through some slides around this. So, it was as varied as satellite image processing to people wanting to troll YouTube to analyze scenes if these are actually birthday scenes. And this is not something that fits within a traditional HPC system. So very quickly, this is the sort of environment that we've got. We've got a user-facing layer on the top, services and physical infrastructure. Effectively, we have these notions of virtual laboratories. It's essentially a one-stop shop, and we then mask everything that's underneath. So this is an example of what we did with Geoscience Australia. So the equivalent, I guess, in the US is the USGS. So what they wanted to do was essentially come up with a unified data processing infrastructure for various data streams, and this wouldn't fit within our HPC system. So essentially, there were Windows VMs, there were workflows that happen on the HPC system, Ubuntu VMs, etc. So that photo, that picture there is something that they weren't able to do before, which is essentially land classification of the entire Australian continent. And mind you, this is done through the intersection of HPC, cloud, and data. So the other piece that we had to sort out was moving climate data sets. So the guys at NERSC were working with us, and we were able to essentially flood a 10 gig pipe all the way from Sydney to Seattle. So, I'll put these slides up, but essentially we've been working in multiple areas, and So the problem was we had to come up with infrastructure that would solve this problem. And effectively, Dell gave us the answer to this particular puzzle. How do you come up with a big data analytics platform that would actually be good for handling good read performance, etc. So essentially, we use OpenStack, and OpenStack gives us the substrate to essentially have clusters as a service. We bring up Windows HPC clusters, and now we're even looking at bare metal as a service. So effectively, we've got a big fat tree system here, 56 gigabit Ethernet, and we've got node local SSDs. So the system's got about 160 terabytes of SSDs in there, and this is from Dell. So I'd like to end by saying what I really like about this is we're able to meet these challenges, and essentially, it's hyperscale meets exascale. So with that, I'll end.
Yeah, thank you, Joseph. All right. So we're going to do the QA portion of this. Before I have some canned questions, but anyone in the audience have a question they want to ask of our panel? Right here, sir.
Have any of you looked at using Linux containers, LXC, in lieu of doing actual virtualization?
No, Joseph's got something. Yeah.
So you need the ability to essentially manage the environment, right? So this is why we use OpenStack. So we're not wedded to the fact that you need to have a particular hypervisor. If a container does this for us, we'd use it. So in fact, we're actually using LXC in test, and we're going to put this into production for GPU workloads. So.
Okay. Any more questions? Oh, please.
I've got an answer to that one also.
Yeah, okay.
So are you a systems administrator at BYU? Yeah, kind of. Yeah. So this is something that we go over because there's a fair amount of overhead, and maybe that's your point in terms of deploying systems through something like... Oh, I see. Okay, yeah. No, well, I mean, just sort of in general, that point, there is a lot of overhead in something like OpenStack or Eucalyptus, and I think you really need to sort of have a use case, and that is, often for us, that is our vision is that the end user will actually be able to access the interface in the same way they do, AWS or, any of these other services, and that we actually don't need to be there. So they can actually bring up these instances without our help. And if we didn't have that vision, then definitely we would go with something that is much more lighter weight for managing virtual machines.
Yeah. More questions? Okay. Well, I got one. I don't know if you folks are aware, but there's this show called VMworld. Just VMware's show is twice the size of supercomputing. That shows you the size of the ecosystem here with virtualization. You guys, are you all using VMware? None of you? What? I lost track. Brad's using it. Is the cost a problem for you?
Only slightly awkward because I spoke at VMworld. So I'll give you the official line, which is as a VMware partner, what that is. Cost could be an issue, I know that VMware would very much like to work in HPC and would like to find a model that's both beneficial to the company and beneficial to the partner, but if its current licensing scheme was applied to large-scale HPC, no way. It would be way too cost prohibitive.
Well, they're going to charge you by the core or something.
Yeah, exactly.
Do that on Titan. That'd be fun.
Exactly. So what they're trying to do is they're trying to find out if there's a model that they can use that would kind of let you do that. But that's why you don't want to necessarily put all your eggs in one basket and look at things like OpenStack like we are and a couple other hypervisors. Because at the end of the day, like it was said, it really shouldn't matter what the hypervisor is. It should matter how it's being managed and how you're allowing that client to do that on-demand provisioning. And at the end of the day, the customer should never know that it's VMware or it's OpenStack or it's Eucalyptus or whatever it is. It's just that it worked. I clicked a button and I said I wanted 10 nodes and I wanted them all to be Ubuntu, and it's done.
Yeah. Any other comments on that? No? Nobody's going to complain about the price. Okay. All right. So, any more questions from the audience? Oh, here we got one.
So how close are we to being able to stand up VMs on multiple nodes, and run a virtual cluster and actually get low latency MPI communication, so highly coupled processors and so forth talking to each other?
How close are we? Who's going to jump up, Joseph? No?
give me a month or two. I'll come back with some numbers. Because what we have right now is we actually have a cluster, which originally started its life on the VMware, right? And we moved parts of, so it was what we call a Franken cluster. Some of it was actually virtualized with VMware because we had complex software stacks that we had to encapsulate. There were bare metal nodes, and these were actually done using Dell blade chassis. Right, so this was, 2 or 3 years ago, and this handled weird and wonderful use cases. Now, and we actually published a paper in IPDPS showing the actual performance hits that you get if you were on Amazon versus an actual HPC cluster and on this VMware cluster. So what was interesting was, it depends on the application, right? I believe with single root I/O virtualization, and RDMA over converged Ethernet, it would be feasible to actually get very decent latencies. So hopefully in a month or two, I can get some numbers.
Yeah, yeah. Well, I know I wanted to ask about InfiniBand. Are you all InfiniBand users? All, yeah. Because that support wasn't there in VMware until very recently, if I'm not mistaken. So the question is, what capabilities would you love to see in virtualization for HPC that you're just going to have to wait for? And do they know about it? Brad? Wish list.
So, I mean, it's obviously InfiniBand, but the reality is, I mean, it's not something that they don't know it needs to happen. They're trying to work on it. It's not a really easy nut to crack. Yeah. And, I think to the last question, there's nothing that would stop you right now from doing this. I mean, you could theoretically run a direct pass-through to your Mellanox card, and it works. The difficulty is that if you want to have multi-tenancy in the same host, it doesn't work. Or you have to use IP over IP emulation, and I mean, it's not ideal. But the challenge I would throw out to everybody is that if you're at all involved in HPC, any one of the boxes from any of these customers, providers, the answer is always, it depends, right? So there is no silver bullet. Like, it always works for all platforms, all solutions. Everything always has a little bit of a caveat to it, and this is no different. In some solutions, it works really, really well, and in other solutions, it doesn't work so well. But the places where it works really well, and I mean, in our opinion, far outweigh the few instances in our environment that it doesn't work out well. And for us, that's why it's really worth taking this leap and trying to do this. And I think the other thing is that there's not a barrier to doing this. I mean, VMware will give you free licenses to test this kind of thing out. And, great companies like Dell will also partner with you to, stand up hardware if you want to do a proof of concept or pilot to see if it'll work in your environment.
Yeah.
So, Rich, must admit, we originally started off with an InfiniBand fabric, right? Yeah. We're a HPC shop. But the risk was too great when it came to implementation. So the route that we've taken is essentially running it at 56 gigabit Ethernet, right? Okay. So flashed everything. It's going to be completely Ethernet, but it's using InfiniBand hardware electrically, right? Yeah. So first stage would be have this working as 56 gigabit Ethernet, use a single root I/O virtualization to get multiple NICs so that we solve the multi-tenancy problem. Now, I'm told that they've been able to solve both the InfiniBand and Ethernet problem, but because of tenancy issues with InfiniBand, we're not going to do that. So how do you get to data very fast? Yeah. RDMA over converged Ethernet, right? So you essentially have TCP bypass, and you essentially, so what Mellanox and, in fact, you can buy Cisco switches, which essentially encapsulates an IB frame within an IB packet within an Ethernet frame. So you can do RDMA. Right? So one of the things that we're actually doing right now is getting our Lustre system mounted directly into virtual machines and doing RDMA over converged Ethernet. Right? So it's not going to be as fast as the HPC system, right? But we will have a similar user experience. Right? So
great. Well, predictions. 5 years from now, will there be any need for a panel like this, or will it just be everybody's just using virtualization? What do you think? Anyone have an opinion? 5 years. Paul?
2 years.
2 years. Good. Terrific. All right. Any more questions? We have one here. Excellent. Thank you.
So, question on the virtualization side: how do you handle, mixed architectures of instruction sets of processors? So, if you want to take advantage of the latest AVX or the SSE, whatever, or do you normalize down to the least common denominator, or do you recompile based on where the job lands? Or do you have a big fat binary?
All right, Joseph's up. Thankfully, I was at the OpenStack conference in Hong Kong a week ago. So effectively, there's a virtual machine, there's a hypervisor called Zero VM, which has come out now from Rackspace. What they've done is they've essentially taken Google's NACL layer, and you have this as a lightweight thread. So the idea is if you wanted to run Swift, compute for Swift, which is the object backend, you'd be able to spin up virtual machines very quickly. Now what they're able to do is, I think you've got a tool chain, so you'll have to recompile here, and it's using LLVM. So the idea is you'd have a JIT which will essentially target ARM or x86, right? And because it's NACL, it's sandboxed. And the idea is you get rid of all of the overheads associated with having an operating system, and you abstract that. Now, mind you, this works as a proof of concept right now, but my expectation is you'd essentially come up with an LLVM binary, which would then JIT to the architecture that you want. Right?
Yeah. Any more questions? Okay, yeah, Chris. There you go.
So, in terms of developing accounting models in Chargeback, you have to measure this stuff, so you can come up with accounting. How much of a difficulty has that been for getting all these numbers?
Okay, accounting, excellent question. Yeah, that's someone else's problem. Yeah.
So on the low end, because we only actually offer that component of our services as a chargeback, we do it in a very coarse-grained way, in a 1-month cycle. So it's not a very good answer, but it's one in which it satisfied a need for us to actually get into that space, to provide the services that I described sort of in my overview. But actually now we're looking at using some of the OpenStack features specifically to do a finer grain look at that, in anticipation that we will be able to turn the interface over to the user so that they can actually deploy their own systems. So that's where we're going. We're not there yet, but in my opinion, that shouldn't be a reason not to start, because you can do it in a coarser grain way.
Actually, this is the main reason why we haven't started, because I do need to charge people in a very fine-grained way. And the development work we're doing is looking at OpenStack and that charging mechanism and integrating it into our pre-existing toolchain. So until that's working correctly, we can't roll it out.
Yeah, Brad.
Yep, I agree. So right now, it's essentially, we're not charging users at the moment. We're waiting for a project called Ceilometer to mature. Yep. So we can essentially charge for IOPS, bandwidth, as well as CPU cycles.
So I guess I'm the odd man out. It does work on the VMware side. OpenStack is harder, to be completely honest. But I think it goes to what your charge model is. So we don't charge by IOP or any of that. We're charging by either sort of CPU hour or by storage, and that's it. We try to keep it really simple because our effort is we're trying to get researchers to basically maybe that are up and coming or just got their first K award that don't have a lot of money. So we want to give them a service where you don't have to spend a lot of money, but you can still get access to some serious metal.
We don't do chargeback on our compute processes. We do for guaranteed resource allocation for kind of support things where we have people who bring in nodes that are peripherally HPC. It's being Oklahoma, we do, for example, LDM to move weather products and those sorts of things are associated with the cluster. So we do chargeback for that. We are developing more accounting stuff, though, for characterization of virtual machine workloads so that we can differentiate the things that people are running that are more enterprise-like versus things that are purely compute, so that we can appropriately stack and overcommit memory resources for the one and not so much with the other.
Yeah. Well, if there's no more comments, I think we're out of time. So could we give our panel a hand? I think they did a terrific job. Thank you. Thanks, guys.